very happy to welcome Professor Vinayak Nayak, who is an associate professor in IIT Delhi, and this semester he is visiting the CSE Department here. And today he's going to be talking about how to apply machine learning techniques to detect physical advantage of people who are traveling on network rails. So, welcome.
Thank you. So that's the title of the slide, and I was debating on which title to put for a long time, and then finally I put this one, because I think, like any of us, this captures what I'm going to say, nothing more, nothing less. But then if you indulge me for a while, then I might change it to something which is easy to take and maybe of interest to quite a few of you. It says smart transportation for smart cities. I think I saw the video of Professor Kriti last time when he was delivering and talking about energy consumption and how to optimize the energy consumption. It's a tough act to follow. He gave a very nice presentation, the last video with the audio very nicely done. But I think one thing that resonates with that, and maybe we carry forward that thread, is he talked about energy, which is one of the very important resources that we have, and how do we optimize its consumption. And if you look at the bigger umbrella or theme of smart cities that everybody is talking about these days, other than the energy, maybe the next one that we can look at is transportation. So, with some loss of generality, let me put this title now, and then slowly walk you through what is it that I am doing, what are the problems out there if we want to enable things for the smart cities, what are the research challenges, what is the state of the art. So those of you maybe are interested, already working on this topic, will get some idea about what things have happened. And those who are looking for or thinking of doing something in this space of smart cities will actually get motivated. Let's see. So this is joint work. Before I start with two of our students, Megha, she is now at Khosla Lab after doing MTech there at IIT. Another one is Anchal. After finishing her masters, she is joined as a PhD student and a faculty at IIT Bombay, Bangalore. So many thanks to them. It's all joint work. Okay. So if you Google smartphone mobility, the first site that you would hit is a venture capitalist site, In Motion Ventures, and this is exactly I copied from them verbatim, and that's the photo. And what it is saying is, in today's world, we have so much of data. We have very good network connectivity, we've got good sensors, we've got good computational devices carried around by the people, and all of that can smartly get combined with all the data availability. And then we can do something which will ease our problems of transportation. And those problems are the vehicle routing, real-time data on congestion, which I'm going to talk about a lot today, roadway construction, incidents, parking availability, real-time public transit options, and so on. There are many of these. But today we are at a point where technology is a good enabler, not only from the device point of view, but also the algorithms and the science that goes along with this. This is also at a very nice junction. And if we combine all of these today, we can derive a lot more than just the sum of these pieces. So let's rewind back and let's go to 2004, and I will show you an example of where the kind of thing I'm going to do, the theme that has been played before again and again, and then we are looking at a different incarnation of that same concept. So this is the person. His name is Lalitesh Katragada. He's an IIT Bombay alumnus, 1990. He was at Google, and Google by that time in the US and everywhere else had already came up with this app called, or a web app called at that time, Google Maps. And it gave all the information about the entire city, the roads, and it would map the latitude, longitude from the GPS to the actual addresses that we write in text. right? So there's both forward and reverse mapping of that. And they wanted to bring this technology to India. And he was the person who was given the charter to do this. At that time when he measured, the cost of what, I hope you all know how Google did it there, they actually hired a truck or some kind of a vehicle, right, with a big camera and a GPS installed, and it just drove around the whole city with all the roads and highways and alleys and so on, right? And that's in a way called wall driving, and they did that. And the cost of that comes out to be about $10 to $15 per kilometer. And when he thought about now doing it in India, right, India's got 3 million kilometers, which translates to $45 million, and every 5 years, because there's a lot of construction, it's a developing country, right? Accidents happen, bridges are constructed, right? This thing, that thing, new localities come up. A lot of things are constantly changing, so doing this again and again. And he realized this is not scalable. So what can we do? So he came up with an app called MapMaker. What it basically does, in simple words, it allows you to go to the Google Maps web application and annotate things on the map yourself, human. Right? So he took humans, and then the human will go and edit and say, okay, this is this road, this is this maybe church, this is this highway, and so on. And he bootstrapped this whole system. There are issues about trust, like whom can we trust in terms of the edits, whom we cannot trust. He built a system around, and in simple words, the way he did it is, at the first level of hierarchy, these are all trusted people. And then these people trust some another level of people, and so on. So if we take care of the problem of the trust, then we could come up with the entire mapping of the country, of the scale of India. Right? And he did that. Right? So in 2006, right, the stage was set, all the test was done, and by 2007 the verification was done about the data that was collected by people, and in 2008 it was ready to roll out, right? And we saw the effect of it. So he did not depend on the maps that are there with the government or with any of the agencies. Right? He did not drive around with a truck with lots of resources. He just leveraged people which are already there and which are knowledgeable and kind of bootstrap this system. So that's one example of how we can utilize people here, right? Or something which is not the infrastructure coming from the government, but still get the job done about the city, okay? In the context of smart cities. The second one, which is like all the systems people or the networking people will probably relate with or already know, is finding location, right? So other than GPS, the other two location providers, if you go and see in the Android operating system, the one is cellular network and the second one is Wi-Fi. And right, the idea is similar, right? Like GPS, you've got these beacons coming from the devices which are geostationary or fixed at a location, and you measure your signal strength and you do a triangulation like that and you find your own location. Right? Similarly, you do it on Wi-Fi. Right? Again here, the idea that is being used is, we don't go and ask the people where your access point is and where your cell phone tower is. We depend on the people and their mobile phones, which has got a GPS, right? And then we measure these other values and we build a map of, when I see so much of signal strength, I'm at certain location. And we'll keep on crowdsourcing this. And as the environment changes, I change my access point, I change my cell phone towers, the system will also adapt. Okay? So this is another example where you can leverage people and right, the devices that they have and their sensors to learn about your environment. And this is the last one, and then I move to what I'm going to do. The last one is the traffic. Now Google Maps in 2008-9 just gave us where the roads are and how to reach from source A to the destination B. But today Google Maps not only gives you that, it also tells you how much is the traffic congestion at different roads in real time. So you can then decide, right, if you want to avoid the traffic, which route to take, and how it is doing it. It is doing it again by using your phones and primarily the phones of the cab drivers, right? Because we don't move that much, but the taxi drivers move a lot. And they're always carrying this application which is running and giving this information to Google. So this gives you live information, real-time information about where the traffic is, and this is again crowdsourced. We are not depending on the sensors in the roads. We are not depending on any of the infrastructure that city provides, but we bring in our own thing, crowdsourced way, and start talking about analytics of how the city is flowing. Right? So I've shown you 3 examples where we don't depend on the infrastructure, but we do something because of the scale and because of the data and because of these mobile phones and the internet connectivity, and get the job done. Okay, now the title, Metro. So if these are the 2 photos, first 2, right, of Delhi Metro, a station in Delhi. If you've been to Delhi, you know the metro is like a lifeline. Like the local trains here, it's the metro there. Okay. So if you're lucky, if it's a lucky day, you'll find the station to be like that. Okay. And if you're unlucky, right, or if you know very well the pulse of the city, right, then you're not unlucky, but you actually see a rush like this. And then the last photo is not from Delhi, it's from Mumbai. This is the Elphinstone station. Okay. And this is not unlucky, this is actually hazardous. Right. So people actually lost their lives there. And nobody knew. Right? This is happening, and then we should stop, and people were just still going to the bridge and so on. Okay. Now, so we have a problem here. We would want to know more about how much is the congestion. And when I say congestion, it's not about the trains and their congestion, they are flowing nicely. I'm talking about the congestion within the train, the people, the human congestion. Now, when we thought of looking at this problem in Delhi to start with, right? We looked at other cities. We looked at Singapore, we looked at London, and we realized they have the infrastructure already in place, quite a good of infrastructure, which gives them this pulse about the city all the time in real time. Right? But unfortunately, it's not there for us in India. And you all know this metro, subway, local train, whatever it is, it's the lifeline of the daily commuters, and if we learn about the congestion of this, then we can do many things. Right? We can understand and tell people that how much is the queuing delay you might expect if you go and stand in a line to get a ticket. We can tell which stations, which trains, which lines are congested, and there are many people entering for whatever reason. It could be a festival, there could be some event on the other end of the city, whatever it is. Right? But we could get this in real time. And then for the public planning, if we understand how all these different transportation, bus, metro, local train, right, they are flowing into each other and feeding into each other, right, these public planning people, the city planning people, can make a better decision about when they build a new city or they want to change the current infrastructure in the city. Okay. And the last point, this is not just about the train, right? We can actually extend this work, and I will show you at the end, to metro, local, and all of that definitely, but also for the bus depot. Right? That is also a public transport widely used, and we can extend that work for the public transport of bus depots also. Now the infrastructure, right? Traditional approaches. We could have used the CCTV footages. There are lots of CCTVs now, cameras installed at a lot of places, and a lot of the train station also use RFID, which is right, your smart card, or the token that you insert into that. So that's there, but there are problems with this. Non-availability of the data. And we went to these corporations, there's something called DIMTS, which looks at the whole transportation system of Delhi. We were running behind them for a lot of months, right, and finally years also, and we gave up. Right? We didn't get the data. And we did not even get the historic data, forget about the real time. Right? We did not get even historic data. And now there are laws in place, like we learned. Right? These will only keep data for 7 days, so we can't get data which is very old and do anything about it. The other issues are, even if you have cameras and so on, right? God knows where those cameras are installed and where they're looking at, right? And the line of sight. And we don't want to depend on that. And then there's a threat to privacy. Once they start releasing all these videos where you can see and track people, and people may not be happy about this. So there are technical issues also, and getting it real time is hard. So what do we want to do for the metro? we want to find out how much time is spent doing various activities that you would do to board a train and get out at a different metro station. And that becomes a proxy sensor to estimate how much is the congestion. Let me elaborate this. So if I go and stand at the ticket counter, right, I stand in a queue and I keep moving, and if I can detect it on the phone that I'm standing in a line at a train station and I'm queuing up, right, if I measure how much is the time I spent in the queue, I get an estimate, a proxy estimate about how much is the length of the queue. Right? And then I walk down the metro station, right, if it's a subway, or walk up, then I climb those stairs. How much is the rush there while I'm doing that activity? Okay, if I can measure that time, right, I get that pulse also. And then on the platform, while you're waiting for the train and you're not able to board the train because there's so much rush, right, you're trying. If we can see how much time you spend there to board the train, we get that information also. And right, you can play it back once I get out of the train and so on. Right? So if I add up all this time spent, I get a rough estimate about how much is the congestion that I should expect at the station. So we are going to detect these activities of queuing up, standing in a line, that is, or walking, or climbing up the stairs, taking an escalator or an elevator, and then waiting on a platform where you're standing. If I can detect all these small activities, right, on the phone, then I just have to measure how much time it is taking for that activity. And metro travel is a case study for us. Right? All the things that I will describe here, the ideas, the concepts, right, as I was saying, will go to other train travel also, and the bus depot, and right, other public transportation also. In fact, right, even the IIT B terminals, right, and as I've seen, around 1 o'clock when it's the lunchtime and all the lectures are over, it's just a lot of rush. People are trying to get into this terminal and it's very hard. Right? And if we have this system, I don't need to instrument that bus, that terminal. I can see the person is standing at the bus stop where the terminal is going to come, and he's trying to, right, maybe there is a queue, maybe there is no queue, it's just rush. We can detect that activity, and once he boards the bus moves on that roadway, right, and we can track that, right, and right, without instrumenting bus and putting anything or depending on the driver to feed in anything, we get a pulse of how, right, what is the congestion on this. So this is one example where we can extend the work. Okay. So, and we can do very fine level things, like for example, we can see how much time is spent before getting into the metro or railway, right? How much time is spent in the queue, how much time is spent on the platform and within the train, whether you are standing or not, right? Whether you are sitting. So we can get these all sorts of micro activities, and when we put them one after another, we kind of know at exactly what place the congestion is. Okay. So I'm going to divide this problem. The first problem that I will address is identifying just you are within the train and whether you are on in the metro station waiting for it, right? And when I say metro station, it includes everything that you do, queuing up for the ticket, right? Taking escalator, elevator, all of that, right? So very two high level activities, right? And I will try to see whether I can do these and divide these into two. And then once, let's say I'm successful, right? And later on we realize the other piece of the thing where we then take this in metro station activity and divide it into further activities of whether you are moving, that means walking, whether you are queuing in a line, whether you are stationary like this, or whether you are climbing. And when I say climbing, it includes anything that changes your altitude, which means stairs, escalator, elevator, anything. Right? So let's see the first problem, and then we'll look at the other one. So before we attempted this problem, we thought of just taking the acceleration, x, y, z. So accelerometer is a device which has got three axes, x, y, and z, and it's a vector in these three directions. And when we plot it like this, on an x-axis we have time, and on y-axis I convert it into one scalar number by x square plus y square plus z square and square root of that. Right? And we decided to see whether there is any hope of attempting this problem. Let's just visually see first whether, right, when I plot it, and whether I see as a person any patterns in this data. And so if I annotated this, right, so in the first one, it's like this, highs, it's a non-train pattern, and then within the train, if you see the acceleration kind of goes down, and it's smooth, right, it's smooth. And then again when I start maybe walking and so on, right, it jumps up and down, and then again this, right. So train has a different signature in terms of acceleration, and when I see when I'm not in the train, I'm doing other things on the station, right, it is a different thing. So there is hope, right? Visually, if we see the data and plot it, right, there is hope to proceed further. Technically speaking, what we will do now, right, we will, if you are aware of, if you've seen machine learning, right, what we want to do is we want to identify the optimal size of a window for which we have to capture this acceleration value, and then select a feature for that. Summarize this window with something. That's the feature, right? So we will try different sorts of feature selection, and then we will also try different classifiers which are available. I'm not inventing any new machine learning classifiers. I'm just taking what's already there and adapting it depending on the problem that I'm looking at, and seeing which one serves us the best. And then last one is we'll address the problem of class imbalance. So classes, you can consider these two activities that I describe as each of them as one class. And when I say class imbalance, when we are collecting this data, most of the time people would spend within the train and not on the metro station and train station, right? I mean, if the journeys are very long, right, that's going to happen. And so we will get data, and this will happen in the real system also, that we have a lot of data from one class as compared to the other one. So how to balance out this effect? How other people have looked at this, right? So one thing, the simplest of the techniques I would say is when we take this acceleration and then we translate this into something which is binary. Right? So you can take a threshold and say anytime the acceleration goes above this is high, and anytime it's below this threshold, it's low. And then I can convert the whole time series of acceleration, the numerical values, into series of h and s, and you will have h, l, h, f, right? Once I windowed the data. So this reduces your dimension, it's just on h and l. And then you can leverage all the data mining techniques that find out pattern. Once the data is labeled, it will find out the patterns among the data for each of your activity, and then that's your solution. But when we applied this, we saw ourselves that it's hard to get any of these simple h and l's, right? And a pattern of h and l's, combination of h and l's in any of these activities. And it's because the data is so noisy. If you've played with the accelerometer on your phone, right, there's so many apps available. You just install it and you keep the phone right steady, still it will, right, it's very sensitive. It will keep on giving you a lot of noise. So with that, all that noise, and you, right, kind of look at only one threshold, static threshold, and working with that, that's not going to give a satisfactory result. So that's one. The other set of work have looked, so this was, you can classify in terms of whether you're looking anything at the time domain, and you use the general stats features like mean, variance, mode, and etc. So that's one way of looking at this, and just utilizing that with your machine learning classifiers. We will do that as well and show you how does that compare to something that we are going to propose. There's another body of work which converts this time series into frequency domain data in a hope to have certain frequency of band when you're doing certain activity. We put a threshold around that. But we realized that we tried to do FFT and put it into frequency domain. We didn't find any threshold, and I think the activities, right, in itself there is nothing periodic in it, right? It's just very erratic movements that we do in the kind of activities I'm talking about. So we didn't find good results after applying frequency domain, and the mean, variance, and mode we'll talk about later. This, the last line of work is about using sensors on the phone, which comes closest to what we do. So they'll use Wi-Fi, GPS, magnetometer, accelerometer. so how does Wi-Fi and GPS? So GPS you can use to see whether you are traveling in a train by looking at the track of the trains where these routes are. But a lot of times the subway goes underground, there's no GPS, right? We lose the line of sight with GPS. Wi-Fi, right? Developing countries, there are lots of Wi-Fi access points, and as you move, right, you can see within the train, you see different SSIDs, different access point names. In India, we don't have that many access points, so we can't depend on the density of access point that can tell us that you are moving or you are at a certain place. Magnetometer, it comes on a very high-end phone, which can detect how much is the magnetic infrastructure around me, and you can utilize that to find out whether you are in a train or not, because train has got this certain big iron structure. But you have to then use very high-end phones that has got magnetometer. We're using accelerometer. Besides the other one, we'll be using the accelerometer, and we also are using barometer. So I talked about that. Okay. Now, as we proceed, the first thing we'll do is we'll see what is our data set, and we'll see what kind of features we can take out from this data, and then what sort of classification techniques we'll apply. For our data collection, purpose of our data collection, we sample the accelerometer at 50 Hz, about 50 Hz. Android does not let you specify exactly what frequency you want because it will vary from phone to phone. But ours was around 50 Hz. We record, this is label data, we annotated this by help of people, which means people recorded when they entered their trains and when they exited their trains, and similarly stations. Whenever we could use GPS to find out whether you are in a train station or not, we use GPS for, and that's automatic labeling. But we also do require people to tag these information when they were collecting data for us. And once this trace is logged, it gets uploaded to a server. Right? We collected about 23 hours of accelerometer reading. This is just right while doing the travel. Right? It's not it's not a day, and within 24 hours we have so much. Right? Whole collection, data collection is 23 hours. We've got 7 volunteers, right? Male and female. The reason I'm saying male and female is because right, they carry phones differently. We don't ask them to right, carry a phone like this and walk. Right? They either put their phones in their purse, backpacks, back pocket, hold their hands, right, talking to, playing games, listening to music, anything. Right? So we had 7 volunteers, and we looked at 9 metro stations, and we selected the one in the center, which are like junctions and which see lot of footfalls, very crowded. We also selected stations which are on the periphery, which are hopefully less crowded. Right? Some are underground, some are on the ground, and some are elevated. Right? So we covered all sorts of metro lines, and we also, if you see, covered different metro lines as the color indicates. So this is to get us a diverse set of data. I talked about how we converted this 3D acceleration into one scalar. This also gives us one advantage, that we don't worry about the orientation of the phone now, how we are folding. Is x-axis pointing like this or this or this? We don't care. Right? It all gets converted into one acceleration. So that benefit we get. Right? So data collection is easy, and then when you apply the model, that's also easy. Binning, I talked about once we have this entire time series, we want to chop off this time series and look at every window of the data and then select a feature. Now, how big the window should be, that itself is a question, and we have to learn it empirically by looking at the data and right, coming back. So I'm going to talk about 20, 30 and 40 seconds. Right? We covered on both the sides more also, but this is in between. We'll see what is the optimum value or optimum accuracy that we see. We also consider overlapping windows and non-overlapping windows, and that's a very subtle point. What is an overlapping window? If you see, this is the blue one is a non-overlapping window. You take one section of the data, and then you see something which is disjoint from this, and this is the third one. So these are 3 non-overlapping windows, and then the gray one indicates overlapping. So I have this data, and then I slide it, and I see this data, and then I slide it, and I this data. And we did all sorts of percentages in terms of sliding. 0% overlap, which is non-overlapping, and then like 99 or something less than 100%, which gives you a little bit of sliding. Now, how does this play a role? This will create a lot more windows of data, and that has a chance of influencing model in a different way that we are going to train as compared to this one, right? In fact, this has more, so if you see this window, the gray one, right, it has some part of data within the train and some part of data in the metro. So you are actually taking from each class some data, and that becomes one window, right? And we will have lot more of these windows, and the probability of this happening is lesser in terms of these blue windows. Okay? So, right, the way model will learn now from our data is different when we do overlapping and non-overlapping. So we will be able to do both. I talked about these order statistics like mean, median, standard deviation, mode, and we tried all of that. So if you see then let's take the mean. If you see the mean, and this is the time, okay, and you're doing one activity at a time, let's say, right? So this is labeled data, so we know which activity you're doing. If you see you're doing one activity, and then this is your second activity, and this is again the first activity. Then ideally we would want this blue to be a different in terms of mean, and this green to be on the different. But as you can see, I see these mean values in green also, and I see these mean values in blue also, and vice versa. Right? So when we took mean and median, and we also tried mode, I'm not showing it here, right? We didn't see a clear demarcation of activities visually, right? And this also came out to be true when we trained the classifiers. So a lot of people that have worked on similar problems before us, they were dependent on these ones. But their problem was different, to be fair. Their problems were not exactly the one that we saw. It was about transportation, but a different one. Okay, now I will introduce a concept of ECDF. What this is we've got these accelerometers, which are discrete values, and we sample these accelerometers, which is a discrete variable, and we plotted the CDF of this, right? We see this ECDF, which looks like an histogram like this because it has certain definite values. Okay? And then what we do is we do a cubic interpolation of these blue line, which is ECDF, and derive a CDF out of this. So we move from ECDF to CDF, that's the gray smooth curve. And now with that gray smooth curve of CDF, we divide it into 20 equal sizes, right? And that kind of gives us the whole distribution in terms of 20 dimensions. And we take those numbers. And we do this for every window that I'm going to do, 20, 30, 40, overlapping, non-overlapping, whatever. That becomes our feature. Right, so that becomes our feature. So we have 20 values, which kind of, intuitively speaking, it is giving us the whole distribution of data for a certain activity within that window. Now, I guess most of you nowadays know all these terms, but just so that everybody understands this, very simply speaking, this is one type of a classifier which is non-probabilistic, which means it gives definite answer whether you are in A class or B class, and it is used for problems which have got two classes, right? It puts a plane or a line depending upon, right, whether it is 2-dimensional, 3-dimensional, and that gives you classification, and it suits our problem because we also have two classes. To improve the model training, right, you can actually project this data using another function. So you take your data, apply a function, and you project it into higher dimensions in the hope that in that higher dimension there is a clear separation. Okay? So we use the kernel function to do that. The second one which we will try is regularized logistic regression. I hope all of you know what regression is when you put a curve within the data, and typically it's linear. This is the log, right, which puts a log curve in between. This is as compared to the one that I talked to you about before. This is probabilistic. That means it gives you probability that this belongs to this class and, or the other class. Right. So we tried that. The regularization means we have a way of telling the model when it's being learned that don't overfeed the data. We don't want a complex function, right? To be easier one than what we want. So that's that. The next one we tried is random decision forest, which is a classifier using another classifier. So you can think of this as a lot of decision trees, which have very simple way of classifying data by looking at just the rules if there is. And then all of these classifiers will be trained with different data, which you can create by there's a technique called bagging ensemble. And with that, all of these classifiers will run together, and then you can employ a voting mechanism among these classifiers, and that's your final output. And that's how the name also comes. That it's a forest, right? Because it consists of many other decision trees. Okay, so we've got SVM, RLR, and RDF. Okay, so we start from there. These are the simple classifiers. Now, if you remember, I talked about class imbalance effect, which means you've got data from one class which is far more. We already know that. Right? Now, to counterbalance or to balance out this effect, before going there, the number is we have about 25 to 30% of your data is for the metro station, and rest 75 to 70 is the train. So now, what we can do? Let's say if we have SVM. What we can do is we can have differential error cost, which means while we are training the model, if it misclassifies something for one class, we penalizes that classifier far more as compared to the other class. So if you consider this is to be our minority class, which is less data, right? We penalize it more if it misclassifies anything in that class as compared to the other ones. If we had same amount of data for both classes, right, we wouldn't have to do that. But we did not have the same amount of data, so we had to employ these techniques to have different penalization cost for misclassification into two classes. Other technique, in addition to this differential error cost, is we create data. Right? Instead of penalizing the classifier, right, we have a given set of data. Then we take the one which is in the majority and we divide this, chop it into equal sizes of subsets. And then we combine this with the minority data, and we artificially now create more data. In this data we do not really see in this combination, but we take out one subset of the majority class and the minority class, and we combine this, and we have one more set of data. Right? Which was not really collected by any user or participant, but we got it done ourselves. So that's the idea of ensemble learning or bootstrapping of the data. And this we play it into SVM or logistic regression. We did not have to do this for RDF because RDF kind of inherently already does this. Okay. Now this is our entire table of what we are going to compare. We've got SVM, RDF, SVM plus DEC, that is differential error cost. We've got SVM and ensemble learning, like the artificial data that I talked to you about. Then we have regularized logistic regression, and we have regularized logistic regression with ensemble learning. So the DEC is only with SVM because that is how SVM can be, it uses penalty. So it's there only with that. That's one dimension of multiple classifiers. On the other dimension, I'm going to look at order statistics, which is mean, median, and mode. And then I'm going to look at a distribution of the data within a window, that is our ECDF. Okay, so simple order statistics or a complex distribution of the data that looks at the whole thing. Okay, and we then compare across this. Our evaluation is exhaustive. We use n-fold cross validation, and n is equal to 10 for us. This ensures that it's exhaustive in terms of the results that you will get. I'm not going to talk and show you all the confusion matrices here because it is just too much, but I will then talk about predictive accuracy, that's one, and then also talk about the true positive rate and true negative rate. But in our papers, we put in plots that shows everything. let's first look at what is the impact of window size.
I have a question.
Yes.
Couple questions. So have you pooled together data from different users?
Yes.
I mean, I wouldn't be surprised if my acceleration histogram looked very different from
Yes.
somebody else's. But
Yes.
you're trying to now come up with one model which
Yes.
will map. Is that a reasonable assumption? Like, that's one question.
Okay.
The other is this mapping just being from the histogram to the label, right? It seems like if you use your sort of global knowledge of, let's say, the railway network, and if you're walking in one situation after getting down from the train, right? Presumably you're going to be doing something that's different from the same walking before you got into the train, right? This kind of higher level semantic information is not at all feeding into your data, right?
So first question, we got multiple volunteers. It's not really all ages and with all body conditions and all of that. But we had different people collecting the data. And not only that, we've got different phone models, because every phone, although it just says Android, it comes with a different, depending on the manufacturer, the model that you're buying, with a different chip, right, which is more or less accurate. So we have different phones also. So that's one. The second one, can you say the question again?
No, even the first one. So the point is not that you're probably able to do reasonable prediction, but
Yes.
maybe you can do much better if you model at the final granularity of
Yes.
a person, something like that. So the second question is,
Right. So let me take on. So there's a student here at IIT Bombay who's doing something with me as part of this research, and we're actually now looking at just taking the phone and its accelerometer, and we're keeping it steady, and we learn what sort of noise that the phone creates, accelerometer, right? And we try to build a model of the noise. The hope is if we can do that, then we can compensate the noise, and then what just comes out is the good acceleration. In this, we've not done that, right? And hopefully that thing can be inserted here as one module, and that could also train us better. And every phone model at least can be handled that way, not the person. Yeah.
so my second question is, if you're getting out of a train in a regular metro station,
Yeah.
without looking at the phone, without looking at anything, I can reasonably guess that the person is going to go down the stairs or an elevator, right? The sort of position of this time window in the bigger scheme of things.
Right.
So
That's
doesn't seem
yes.
right.
So when I talked to you about those first two classification, right, that was kind of a hope. That once I get off the train, right, it's just all the activities, right? But then people say, there's some criticism from other side that I could be just loitering on the metro station, doing nothing. Just walking around here and there, looking at newspapers, just drinking my coffee and waiting, right? And that, you would take that as congestion, because what you say, your time is spending on the station. So that's not sufficient. So we need to get more micro activities even on the station, right? And you're right? If we expect that this will happen, and that knowledge can be utilized, yes, that's good. And that will also definitely improve, right, what I'm going to present. Right, so about this, so impact of window size, right? If we take very small window sizes, what has happened is we fragment the activities, one single micro activity also into multiple ones, right? And that does not give us a good feature or data to learn anything about that activity. Right? And this is at a very high level, intuitively speaking. And if I have a very longish window, that's going to combine multiple different micro activities into one. And then whatever the classifier now learns, it's about that. So that's how, right, we should not have very small also and very large also. And we learn empirically that 40-second is a good window size, right? And I'm showing you the data. This is not the best data, but overall all the classifiers agree on that. And no matter which classifier we chose, in order statistics or ECDM, right? This window size turn out to be giving us the maximum accuracy and the best results. And the other part is overlapping window and not overlapping window. Finally, right, so there was a little bit of difference. As in, if we say in metro, having a window with 10% overlap rate performs a little bit better, right? But non-overlapping window perform better for the in-train, right? And all the higher overlaps perform far worse. And I think the reason is you kind of, like I said, you take the in station and the metro, right? And that gets combined a lot more. And that confuses the classifier when it wants to decipher between two classes. Okay? So overall, non-overlapping window, right? For all practical purposes, serves as the best. And thankfully, it's also good because this allows us to give you real-time data. We just have to wait for one window, and then we immediately tell you what's going to happen. Okay? So that worked out in our favor anyway at the end. Okay, now between ECDF and order statistics, as you already seen visual graphs also, it did not mean and median, right? And after doing all that exercise, after all said and done, right, we've seen the statistical features does not do well as compared to ECDF. We need, right, far more information about the whole distribution of the data. You can't summarize the whole thing by just looking at one value, just mean or median. Right? You need that distribution. Other thing is, if you see here, the RDF, which inherently has got ensemble way of looking at the data, right, works better. Also, if you do SVM plus complement this or add ensemble learning to this, that also performs better as compared to the other classifier. So yes, you have to take care of the class imbalance problem and deal with this beforehand when you decide on the model. So this is accuracy, and this is the true positive rates and true negative rates, and this also did better here. For the order statistics, the values were very bad. So we just look at ECDF now, and with ECDF, right, the accuracy is also good and true positive, true negative. All the confusion matrices, right, we saw. This comes out to be the best one. Okay, how much time? I have 10 minutes, right? I have quite a few slides, but let me now, look at this, right, briefly. So, I'm not really pitching my work against whatever accuracies these people have seen, but these are kind of selected papers which looked at very close problems. So, the first one talked about transportation mode detection on the smartphones. And the problem was different. What they did is they want to classify whether I'm walking or riding a bicycle or going in a vehicle like a car or taking a metro, right, and identify that. It's not about these small micro activities that you perform while waiting for the train, right? But yes, they have one activity which is the traveling in the train in the developed country. Right? So the precision and recall that they saw there, right, among their classification is that, and what we saw is this one, right? And between 2013 and now 2018, we've seen gradual improvement on these values that are being reported in the papers. So right, we are very fast moving towards getting, because the data is more, right, and the models are there, and you learn more about what accelerometer is. So that's that. The other paper, again, it's one representative paper in this entire body of work. In 2015, they looked at while you are traveling in the train stops and then starts, train stops and then starts. So their question was to identify how many stops and when the train stops and when train is moving. Again, it's not the same as us, but right, they did not report the precision and recall, they reported accuracy, and that was the number for them. Right? But they use magnetometer and other very high-end sensor. Okay, so those are the findings. So accelerometer has got very good potential to differentiate patterns in your data, to identify these two classes, whether you are in the train or whether you are on the metro station waiting for the train. Right? We've learned that the ECDF works better as compared to the simple order statistics, and we also learned that you will probably, right, depending on your data collection also, will face the problem of class imbalance, and when you compensate for that beforehand, right, you will see a far better accuracy. So that's the first. Now there is a whole body of whole thing about, right, what is the second thing. So which means taking now this in metro station activity and then dividing it into moving, queuing, stationary, and climbing. Okay? So I will very fast go through this because we don't have time to go entirely in detail about what is happening. So let me give you these pictures first to show you. When I say moving, it's a walking in the stage. The queuing is like this. Stationary, right? You're just waiting. So this is maybe not the right picture, but stationary means you're just waiting on, right? We typically don't stand in queues. At least I think in Mumbai, we don't stand in queues to get to the train. And then this is climbing, like stairs or escalator, elevator, anything. But very high level. Okay, now our classification is different. We've got multiple different classes. Right? We've already identified whether you are traveling in the train or not. So that is away. Now we just look at the other things. Right? So we need a classifier which can classify into these 4 classes. Okay, that's one approach. We just take one classifier, one model that learns about these 4 and gives you. The other one is the kind of approach we started with, like step 1 and step 2, which means I first decipher one class, give it to another classifier. It will again determine one class and separate it out and give it to the third classifier, and which will take out the other class, and what remains is the last one. Okay, so that's the approach we can take. So here we did that comparison. And the first one, of course, the barometer was very accurate to determine whether you are taking the stairs or going in escalator and elevator, and that was the easiest thing to do. Right? We did not, because when we tried to use accelerometer to find out whether you are climbing on the stairs, that confused us with all the other activities in the station. Right? So we just use barometer, and that's our level 1. So this is again the time plot. On x-axis you have time, this is the altitude, and we see the barometer can kind of gives you indication, visual indication that you can differentiate between these two. Now for the other activities, the 3 classes, if you look at accelerometer again, right, there is one which is queuing, right, this yellow, the green one is the standing, and right, the blue one, the lines which are not really visible here, this is all blue, it's the moving, right? Yeah, so this is also moving. So you can see moving kind of jumps the acceleration up and down, up and down, up and down, right? A lot of variation. But when you are queuing, you kind of have this much variation, and when you are standing, your variation reduces and it sits in a smaller range. Right? So this thing is standing, right? Very dense and very less variation. Queuing is little above, and then the moving is just ups and downs. So this is how it looks. Let me directly tell you what we will do and give you the result. We'll have one approach. We'll take the whole flat model and run it for 4 class classification. We will again try different classifiers and compare results across it. Other one, the hierarchical model, where we start with one classifier and do it into 2 classes and then go to the next level, and so on and so on. So this is climbing. If you're not climbing, you're either moving or not moving. If you're not moving, then you're either stationary or queuing. Right? So this is how we'll play out. Again, we'll try different classifiers. We did the data collection. Right? Eventually, what we learn this, so our accuracies are not so good as the first step. So, our accuracy is 75.2%, and precision recall and calculate the F-score, it is this. The window sizes become shorter because all these activities are kind of smaller in time scale, and we found out that at level 1 with barometer any classifier works because it's easy. SVM works good at level 2, and MLP works good at level 3, and this is definitely better than just having one flat model and one classifier putting into 4 different classes, right, which is giving us 58% accuracy. So now, we do this, we define again what is the window size for within this activity and what kind of classifiers and what we do for each of these levels in multi-level classification. Okay, now in the last 3 minutes, let me again bring you back to the title slide of smart mobility. Yeah. So, if I look at the smart city and what kind of things will enable me, so energy you have seen, transportation I kind of talked about. Right? There's other piece of work I'm working with some of the students and faculty again with Vishwanath there in Roped is using taxi routes to reduce your travel time. Right? Getting this data from the taxi trips, let's say Ola and Uber like, right? And we are leveraging that, putting in these classifiers to understand how can we reduce your travel or transit time when you're traveling. By the way, there is something called Uber movement, so where Uber as a company is releasing publicly, after anonymizing the data, releasing it for people. Right? We don't have a city there yet from any of the cities in India, but for other parts of the world they are releasing this data, historical data, with all annotations and so on, when the trip started, when the trip ended, what was the GPS route and everything. Right? It's a huge amount of data. I hope now very soon an Indian company like Ola will also do it. So that's the transportation. Then there is other piece of work I've worked on for city planning, where I've found out what are the human places of interest, PIO, using again the mobile phones, where people work, where do they go for shopping, right? Where do they go for their education, right? And all of that. By just looking at your smartphone traces, right? We could derive that. The similar line is this, for the environment, looking at air pollution. Another thing that I'm doing with Microsoft Research here in India, and I've done this in LA, when I was at UCLA before, is pollution is going to be a big problem. It's already very bad in Delhi. I think Mumbai is also very fast catching up. We don't have that many air pollution sensors across the city. Right? So even if you get something, let's say for the Mumbai airport, what is the pollution you are experiencing right now on the campus here, you don't know. Right? But now these pollution sensors have become COTS devices. It means that commercial off the shelf. You can buy it for 10,000 rupees. And you're getting far more. People are actually buying it for their homes. In Delhi, when they buy an air purifier, right, very soon it will come with an IoT device that will send it back to the company. What is the pollution? Now, if you have such a dense deployment of pollution sensors, you can actually use regression in between and estimate what is the pollution you are facing. If you are suffering from any of the breathing issues, if you have asthma, you have allergy and so on, right? I want to know what I will experience when I travel in the city. And I can leverage all these other sensors which are around me and give me an estimation for my trip and not what is at the Mumbai airport. So that's that, and we are also doing something here at IIT Bombay with Umesh about what is the computational requirement to do this, to make it possible. Healthcare, right, is the other dimension for the smart cities, and again leveraging phone and IoT devices. We've done a study for the big outbreaks in Ahmedabad in Gujarat, and we reported again using the tablets and the phones. For building, yes, we looked at the smart buildings. I've done something that leverages what are the public events happening. Just by using the phones, you can understand where the events are happening and what is the participation level. We are also working with today's large scale. The whole of this campus is lit up with Wi-Fi. So many access points. There is a controller architecture which controls all this. Now, how can you leverage this without modifying the phones, without modifying the access point, but still give you indoor access? So you can say that I am at this corner of the auditorium as opposed to the middle or the end. Right? So that level of accuracy, but just using the Wi-Fi. Right? So we're doing that. So all of this is actually feeding into this idea of smart city. Okay, that's it. So my office here is 306 in the Crescent building, and my email here is this one. Right. So if you have any questions, if you want to talk about any of the things I'm doing, right, feel free to stop by my office or drop me an email. Thank you.
We'll probably take a couple of questions.
So maybe I can ask a question. Yeah.
Sure.
So the talk was, I kind of kept it at very high level and not went into detail about machine learning. So how was it? Were you able to understand the concepts and get the higher level things? Okay. whatever knowledge of data science that you have.
Did you not have the snacks? Speak up, you're not able to get it. Yeah, so I have one question,
Sure.
right? Which is the question of trust.
Mm-hmm.
So why should somebody, I don't know, install your app or allow you to?
Question. So the way the big companies are doing it is, right, when you buy an Android phone, I think you just scroll through the whole terms and conditions and everything, and you just say accept. Right? There is a very fine, right, print there which says that we will take your data for this Wi-Fi localization and cellular tower localization. We'll take care of the anonymity. Right? So that's the thing. For the Uber and all that, when you are using this app, they ask you for your permission. We will look at your location while using the app, or while you're not using the app, or after you have run into another app and all that. So I think once I get benefit out of that, and there is a guarantee that the data will only be looked at for that perspective and it will be anonymized, then I'm okay. So for example, if I start giving you the trip details when you plan in the local train and saying if I want to go to CST, right? And if you tell me, okay, which is the right time I should go for, right? And you're benefiting from the system as an output. When it is congested, when the train is not congested, I think at that point, with that incentive, you would be okay with sharing your own data as well. Right? That's a give and take.
Yeah, a non-technical question.
Yeah.
So we are talking about smart cities, city planning.
Yeah.
What is the enthusiasm of the government to actually deploy, make use of such analytics?
And so I'm not the person who is in the government, so I can't really say from their perspective. I think a lot of debate, first of all, we have to answer about is what does a smart city mean for a country like India? See, we kind of understand now for a European context and maybe Singapore and maybe in the US also what they mean, what is the lifestyle they have, what are the things and right things they expect. But I guess for a city like, or the cities in India, right, we have to first define this. And I think you've seen those photos when, right, there is very bad rush and people are still trying to climb up the stairs, right? Those are the things. So it's not about, right, how much time you save, but actually you're saving lives there, right? And so for example, even aged people, the old people, they want to travel by train. Or somebody with some health conditions, they want to travel by the train, right? They definitely will benefit a lot more. I think getting that analytics is important, and I think people will also start demanding, or otherwise, so once they start demanding and with the technologies there, I think all that factors will enable finally. And once we see the benefit coming out of that, so now we've already kind of seen that Ola and Uber, right? You just want to ride a taxi, then you don't worry about it. As compared to 10 years back where you worried a lot about it. Right? Once you start benefiting out of it, I think those analytics, right, we will get more and more of that. Yeah.
Very thank you. So, what happens when I actually sit on a train, get onto a train and the train accelerates? Will my phone actually show me that I'm accelerating?
Yes,
or
yes.
is it because of the inertial frame that I would...
So there are two components. One is the train acceleration, right, as you're moving, and that you would see also while you are in the car and other things, right? But there is also another where there is a jerk, right, as the train moves up and down, right? So there is another, right, that has a different frequency, right? So both of them will get combined, right, and you will see an effect.
So I've tried this on an aircraft and it actually does. So what I'm just curious about is why not actually... So a person who's actually just walking around the station can't accelerate at 5 meters per second or 10 meters per second as much as the train.
Right,
so
right.
why not just use that?
So that is fine, but a lot of times the train really moves slowly, right?
But initially you start off with a huge acceleration.
Huge acceleration, right? So that jerk, right, and that kind of gets us that classification. So we don't need to then, once we detect you are in the train, that will happen very soon, right? We want to do it as early as possible, and once we do that, yes, we don't have to do that.
Yes, so isn't this all of this overkill because you don't have to actually put in a classifier, you can just make out from how high the acceleration ends up going.
So we were interested, first of all, right, to detect that how much time you're spending on the station, right? And that has a pattern which you will also see in a lot of other transportation activities, even within train, right? I understand when the train is really moving fast and all that, but while you are riding in the train and train is kind of slowing down and all that, that has an overlap as to when you are walking, right? Similar overlap happens also when you are riding a car, right? At a lot of traffic congestion and so on, right? You will see this overlap coming in.
So,
So you have
so just adding a train may move fast and may not accelerate. Right?
that's kind of the thing. So we want to not preclude any of the right possibilities. Right, so we just decided with that. But yes, once it's in the train, right, we can use a history of that, and you are accelerating at a very high rate, right? So you can't be doing that on the street. Yeah. So that helps. So that can be added.
If a person is inside the train but is moving, like sometimes people
Yeah.
have to move within the train.
Within the train, yes.
So will that thing come in the app or is it not a part
We
of
are
it?
not detecting that in this piece of work, what kind of activity you do, right? But that is another micro activity that you might do while you are in the train, and which can also be interesting that whether you got a seat or not, or whether you are searching for a seat. Right? So that is one. I showed you one paper which talked about when the train stops and when the train starts. Right? Maybe I think right, it falls in that. At what other activities you are doing even within the train. We did not look at that. Yes. So our app will not. So to answer your question, our app will not tell you that answer.
But it can be done using that stop and start thing, right? So when the train is stopping, at that time the activity has to be there. People will move about.
Yes,
But
yes.
if a person is still moving when the train is moving,
Right.
so at that time that means there is more congestion, so the person has not got the seat.
Yes, yes.
So it can
So
be-
yeah, if we get to that micro activity even within the train, right, we could get more analytics about what's happening inside the train. Yes.
You had a class queuing. Whether
Yes.
a person is in the queue.
Yes.
So a queue may move fast or a queue may move slow.
Yes.
So the queuing thing will be a part of the moving run of the station.
No. So that was the challenge. Looking at these two classes separately, like deciphering or dividing into moving and queuing, that was the challenge. So the stationary was easy. The climbing up was easy also. Between these two classes, right, we had the maximum amount of struggle, because when you are queuing up, right, you are still moving, but that movement is not as smooth as right you walk. So when I say move, it's really walking. There is so much of congestion, right, and you are kind of almost moving in a queue, like a queue, right? It overlaps.
But sometimes each person moves every 1 minute or 2 minutes in a queue. So won't that become confused with the stationary class?
No, so if we are really stationary, right? So all these classes do have overlaps. I'm not saying that we can decipher them with perfect boundaries. They have overlaps, but so the stationary is really stationary for us, like this, right? Which, right? And the queuing, although you are standing, right, there is minor motion, right? And once you move in that, right, you get that. We've not used the Markov chains and right model that with any of the hysteresis, which means that once you are in the queue, right, that information goes to the next state, right? Our thing is not that. So right, so that's why maybe the accuracy is less there. Right? If we feed that into the system, right, and we learn and remember that will also improve accuracy. Yes.
Yeah, my question was, quite relevant to the train signaling. So suppose, you have divided a complete journey into 4 parts, like, a user is queuing up, climbing the staircase, then entering into a train and getting an end at the, basically the destination. So what if it will happen, if the journey starts and the train halts for 2-3 minutes at the signal. So that 2-3 minutes time will it get added up into a complete journey? I mean, what will be the scenario for this?
Right. So once the train completely stops, right, and then what she was asking.
I
right?
experienced around 120 to 180 seconds of signal when I travel with the local Mumbai train.
Yes. Right. So it comes to that her question, and apparently when the person, so we might then say this is stop, right? You stop, right? We will not say you move out of the train, because we kind of have that signature when you step outside the train, right? You come down to a platform, right? That particular activity, right, is train or classified as train for that. Okay, but within the train, yes, it might get confusing. Once the train stops for a long time, right? And when the person starts moving, right, we can say it's moving or it's standing, and we say, right? So all that is it's there. So we haven't considered, right, all these minute, but yes, that's why the work is not fully complete yet. Yes.
All right, no more questions. So let's thank Vinayak once again.
Thank you.